And we're recording at last. All right. Okay. So dealing with stability of fixed points after. Okay. I have some good chalk here. Okay. So we're still in section 6.2. So theorem that I stated last time. A is n minus n. Eigenvalues satisfied with the real part is negative for all eigenvalues. Okay. And that means that norm of e to ta, which is just the maximum entry in e to ta, is bounded by this. Okay. For all t. Okay. Now something went wrong. To whoever's watching. Okay. So all I could do, since I've written so much since it stopped taping, is briefly go over this again. Sorry, guys. Okay, so this is a theorem from section 6.2. This is theorem 1 in the notes. That's labeled linear stability. So you have a statement of that in the notes down to here. That if A is eigenvalue is all negative real part, then A will satisfy these conditions, and 0 is a Pauling stable fixed point. So when it was start to proof, A has these eigenvalues, these real parts are negative. Therefore, all the real parts are less than minus m for some positive m. Therefore, rearranging this, m plus aj is negative. So if I look at all the entries of e to the mt, e to the jt, where j is a Jordan form of a, then they all have this form, and m plus aj is negative. So we have a decaying exponential. Therefore, all of the entries of e to the mt, e to the jt go to 0 as t goes to infinity. So that's my very quick recap of what happened there. So you can take a little moment to digest that, and I guess I'll have to keep glancing at the computer and make sure that this isn't happening again. Oh, great. Let's just let that charge later. And I've dropped my phone a zillion times, and I've been lucky enough to not even have so much of the screen crack, unlike practically every single one of my students. And I like to keep it that way. Okay.
Nothing would.
I haven't cracked one, believe it or not.
Oh, okay.
I have not cracked a phone screen.
Me neither.
Show off.
Yeah, but me.
Well, I got my
Yeah,
story.
one of the few apparently. Okay, so because it goes to 0, that means for some t naught, but if there's some threshold at which all the entries of EVMT, EVJT are 1, since all the entries are decaying to 0. So we know that such a threshold exists. So EVMT is this number, I can pull that out. So I can just move that to the other side. Okay, so now I have that inequality, which somewhat resembles this inequality over here, which I know whoever's watching cannot see this, but so we're going to be able to get to that point. All right. So now we want to bound. We have a bound on e to the jt. We need a bound on e to the at. Its norm. Okay. So that would be p e to the jt p inverse. Okay. Now, normally in doing matrix norms, you could say the norm of a product is less than or equal to a product of the norms. But this is not that kind of norm because it doesn't satisfy that submultiplicative property. Since the norm that we're using is just a maximum entry, we can make a similar statement. We can say that the norm of a product is less than or equal to n times the product of the norms. So I can pull these norms apart, like break this one off, and I get a factor of n. And then the n comes about from just a matrix multiplication product. You're going across a row and down a column and multiplying n pairs of entries and adding them up. So that's where that factor of n comes from. And then I could do it again. So I have n squared, norm of p inverse, norm of e to the jt. And these norms are numbers, so I can move them around however I want. By the way, from any other class where this has come up, who can tell me what is this expression here? Norm of p times the norm of p inverse. That is known as the what?
The one
No.
more? It's P inverse should
610 people should know.
Can we have a hint?
be identity.
Wait.
Okay, so norm of a matrix times the norm of its inverse. That's a certain measure of sensitivity.
Oh, never mind. That sensitivity didn't bring it back.
P inverse should be.
I'm thinking, but I'm not gonna be able to get. I'll probably sit here for like 30
I
minutes and then be like, okay, now I got it.
We're
but-
fogging out. Is it a big something like a faint? Is it something like we should remember?
Well, I'll keep off nothing 610, but that was a while ago, I know. It's a condition number.
Oh, no.
Oh,
Is it
we don't
that
have
K or
that
something?
one.
Yeah.
Oh,
Yeah, okay.
Yeah.
I used that like one time.
On the homework problem.
Yeah,
Mormon wants.
it came up on one homework problem,
Oh, please. Okay.
and I did not understand the homework.
I like that one.
I didn't.
Okay.
I'm the one who chose to do the theory homework at the end.
So I'm going to take this whole thing with the n squared lumped in. I'm just going to call that capital K. And this is less than e to the minus mt. So this whole thing is less than or equal to this constant k, e to the minus mt. So that proves the first inequality of the theorem.
So what is the condition number again?
Oh, the condition of any matrix is norm of a matrix times the norm of its inverse. And the idea is, if you have a system AX equals B, and there's a perturbation in A or B, then the error in the solution X can be amplified by the condition number. So the larger the condition number is, the more sensitive it is. Yeah. So those of you who take 561 next semester, it will come up then. Okay. All right, so that's the first inequality. Now we need to look at the second inequality about e to the at times x. Okay. Now, here I do not have a matrix norm, I have a vector norm. But this is just Euclidean length. So for convenience, I'm going to square this. So all this is a sum of squares of all the entries of this vector. Okay, so I'll just go ahead and write that out. All right, so we have e to the atx, which is a vector, ith entry, and we square it. But now I'm going to write this out in terms of matrix vector multiplication. Okay. So this entry of this matrix vector product is sum j equals 1 to n, and we have e to the at ij xj. So that's just the definition of matrix vector multiplication gets me to this. Okay. Now, here we have individual entries of e to the at squared. So, oh, did I forget a k in here? No? Ah, dang it. Okay, hold on a second. Because I was supposed to have, okay, yeah, I need a k in the final result. I just forgot in the notes. There was a mistake in the notes, but I'll fix that. So each one of these entries is less than or equal to k e to the minus mt. So I can say all this is less than or equal to, now keep in mind it's inside a squaring, so I got to square all this, k squared e to the minus 2mt, and then I still have everything else in here. Xj squared. Okay. But if I take the sum of squares of a vector, its components, and add them all up, that's the
For being so.
close. Well, actually, if you think of a vector as a matrix, then yes, it is. But it's also the vector 2 norm.
Smart, just.
Oh, sorry, that's not xj, that's just x.
What does your J start at? J equals what?
Oh, 1 to n.
Okay.
Okay. And then I have this meaningless sum over I that's not doing anything. Well, that's just going to give me a factor of n. So what I get is n k squared okay, that's strange. Alright, dang it. Okay, n is k squared e to the minus 2 mt. The thing is, this is not working out as conveniently as I wanted it to. So for one thing, it would be nice to have another factor of that, because and then I have norm of x squared. Now this would be a whole lot nicer if I had,
N squared.
yeah, it would be, but I don't seem to have that. Okay.
So, won't you get N squared because there are like two sums?
Well, the thing is, one of the sums
Maybe
just
just
gives
one.
me the norm of x. Okay, and then all right. Now unless I'm getting something from the, well, no, I just have these individual entries of e to the at. Okay. I'm so sorry, I'm going to put the thing. Oh, actually, they don't even. Okay, well, first I want to check my norm definition. Yeah, so norm of A times X, any matrix A, is. Oh, that's weird. N times the norm of A times the norm of X, except that's the Euclidean norm. Okay. So then, but if that's the standard Euclidean norm, I totally disagree.
What was-
Somebody got that called on purpose. Like that.
I totally disagree with her inequality in here. I mean, I'm not saying it's wrong, but because what they have, the inequality that they're relying on is that, and I'm going to square everything. So the norm of, for any matrix A, squared is less than or equal to n squared norm of A times the norm of x. Okay, so what they have is identical to what I have, except they have one more factor of n than I do. Now, what you could argue is that since n is a positive integer, and since I have less than or equal to,
It'll always be less than equal.
I can always do that, and it won't affect anything. It's cheesy. So because then really we're making a conclusion that's weaker than what we could make. So that would suggest that the norm of EVAT x is less than or equal to nk e to the minus mt norm of x, when really I could just as easily say square root of that. And that would also be a valid conclusion. So the dang book was jerking me around. But it's nice to know that what I had on the board was at least correct.
Dr. Lewis, it doesn't matter if n is positive or not.
Negative,
Well, n is a dimension of a matrix.
So it has to be positive. But
Yes.
I mean, it'll still be less than equal.
As long as I have absolute value, yeah. Oh yeah, that's because it's an integer.
Yeah.
Okay, so since we don't have matrices that are sized like a half by a half, then we don't have to worry about that. Okay, so last part of the proof, and I definitely can't wait to get this one over with, considering how chaotic it's been. Am I still recording? Yes, I'm still recording. Okay, so now that proves the second inequality of the theorem, and then the only thing left to prove is to show that 0 is an asymptotically stable fixed point. And that means we have to show that the flow goes to the fixed point, goes to 0, as t goes to infinity, at least for x in a ball around 0. But in fact, because it's a simple linear system, we'll be able to show something much stronger than that without any effort. Okay, so I'm going to let epsilon, I'm going to do delta epsilon proof. It's a review analysis, guys. Okay, and I'm going to let delta equal epsilon over n squared k e to the minus t naught times a, where t naught is the value that I came up with earlier for all the entries of e to the jt being sufficiently small. Okay, so now I'm going to look at the flow to x at time t, but since it's just a linear system, really I'm looking at the difference between this and 0. But that's just going to be the norm of e to the at times x. Now, based on matrix norms, that's the same as n e to the at norm of x. But let's see. Actually, I didn't want to do that just yet. I'm going to rewrite this matrix here. So this is still equal. So e to the a t plus t naught. And then to compensate for that, I have e to the minus a t naught times x. Okay. Now what I can do is say, I can break up this product of matrices as long as I have a factor of n included. So I can say this is less or equal to n, and I'll pull off an e to the minus t naught a. Okay. And then I still have the rest of this here. T plus t naught a times x. Okay. Now, okay. Now I'm going to assume that the norm of x is less than delta. So now what I have is, here I have this expression, e to the time value times a times x. For this, I can use this inequality right here. So where instead of t, I just have t plus t naught. So that's going to give me n squared k, this expression, times e to the minus m t plus t naught times delta, which has been bound on the bound to the norm of x, because we're assuming it's less than delta. Okay. Now I have n squared k, this norm times delta. By rearranging this equation, what I get is this is less than e to the minus m t plus t naught times epsilon. But this is a exponential of a negative exponent. So this whole exponential is less than 1. So the whole thing is less than epsilon. So what that means is 0 is a stable fixed point. Okay. Okay. And the thing is, because this flow, e to the atx, so my last remark that e to the atx goes to 0 as t goes to infinity for all x in Rn, not just x within a ball. So because of that, this is asymptotically stable. Because in order to show asymptotic stability, we have to show regular stability first. So that's why I went through all this. Okay. Okay. And that completes this way too long proof about linear stability. So we have all negative eigenvalues, zeros are asymptotically stable fixed points. Okay, so limit as x goes to 0. Okay, gotcha. All right, so questions about all this mess? Okay. Now, I'm doing on time, still taping, good. Okay, 35 minutes. So, between that and the other results that I stated last time, which I'm not going to bother to prove, we now have a picture of what's going on with linear stability at fixed points. It all depends on the eigenvalues. If you have all negative eigenvalues, 0 is a stable fixed, asymptotic stable fixed point. If there are any positive eigenvalues, then 0 is an unstable fixed point. And then The only other possibility is what if all the eigenvalues are purely imaginary? In that case, what you generally have in a linear system is 0 is a center, that you have like circles or ellipses that are orbiting 0. Okay. Whoa. Okay. Now that's linear systems. Now we need to talk about nonlinear systems. And fortunately, we can piggyback off of linear stability to talk about the nonlinear case. All right, so this actually gets us into section 6.3. Okay. Which actually there's not much in this section. Okay. So if we have okay, so a proposition. If we have two systems, x prime is big X of X, y prime is big Y of little y, and these systems are topologically equivalent. Meaning that big Y is the push forward of X by F. Was it you who were saying that you wanted to do this in class?
was.
Did you do that?
No, I didn't text him.
Yeah.
I would have texted him way before now if I knew it was on.
I totally would have.
Yeah. How's Diana? Okay. So let's put forward F, where F is a homeomorphism. Okay. And we assume that C is a fixed point of big X. So what that means is, if I define B to be this homeomorphism applied to C is a fixed point of big Y. Okay, so because solutions relate easily through F, and so do fixed points. So it turns out that C and B have the same stability. So if systems are topologically equivalent, then their stability at fixed points is also equivalent. So we can say that C is, I'll condense this, either stable or asymptotically stable. So you can pick either one. If and only if B is. So C is stable if and only if B is stable. C is asymptotically stable if and only if B is asymptotically stable. So stability just carries over. And now we'll go ahead and prove that. Well, in fact, the first thing I'm going to prove is a little result, because there is a homework problem from chapter, earlier chapter, maybe chapter 3, that I did not assign, but still had a conclusion that's worth knowing, so I'll just prove it here. That if you have a homeomorphism F that relates these two systems, and you have a flow of this system, is there an easy way to describe a flow of this system in terms of this flow, and also in terms of F? And you can. So I'm going to do that first, and then we're going to need that flow in order to prove this equivalence of stability. And the way we're going to use this theorem is, like, if one of these systems is linear and the other is nonlinear, well, we can easily determine what's going on with fixed points of the linear system, and then we can say that the same thing is going on with the fixed points of the nonlinear system. Okay, so let's see how torturous this proof is. Okay, so first, I'm going to define the flows for x and y. So I'll just use these superscripts to indicate which flow I'm talking about. Okay. Now, I'm going to let alpha is integral curve of x. Okay. And then I have, I'll let x, little x, be alpha of 0. And then, what that means is, beta of t, which is f of alpha of t, is an integral curve of y. And I'll let little y be f of x. Alright, so we have integral curves for each system that are related by f. Okay, so now what I want to do is I want to define what the flow of y is in terms of the flow of x. So, say, what is the flow of y? Plugging in little y. So little y is basically serving as the initial data for this integral curve of y. So this is a value of the integral curve at t. Well, that's beta of t. Okay. But what is beta t? Beta is alpha, is f of alpha of t. So right away, I can relate this to a flow of x, because alpha of t is the flow of x with little x as initial data. With me so far? Now y is f of x. That means I can write x as f inverse of y. Okay. Oh, actually, is that all I want? Yes, that is all I want. Okay, so that is my, that's how I can define the flow of y in terms of the flow of x. Because I'm always evaluating the flow at some point in y space. So I take f inverse first, take the flow of x from that initial point, but that puts me in x space, and I use f again to get back to y space. Okay, so now I can focus on the main part of this proposition. So I'm going to assume C is a stable fixed point of x. And I'm going to show that B, which is f of C, is also stable. Now this is an if and only if proposition, but there's really only a need to prove the if just because to do the only if. The steps are so similar, it's like, why bother? Okay, so I'm going to let epsilon remain 0, and the thing is, f is a homeomorphism. What do we know about a homeomorphism? What properties does it have?
Both f and f inverse are differentiable, is bijective, and all that stuff.
Well, it's not all the stuff.
Well,
It is
it's a
bijective,
whole list of stuff.
yes, but now it's, yes, injective,
No,
surjective, so it's bijective.
the differentiable is the diffeomorphism.
Right.
Oops.
So what property does this have instead of differentiable? Yes, it is continuous. Okay.
a question.
So what that means is there exists some epsilon naught greater than 0, such that we have this relationship that if we take a ball around C of radius epsilon naught. Now, if you want, you can think of epsilon naught as kind of playing a role of a delta. I'm not calling it delta because I need delta somewhere else. So what happens is, here we have all these points that are close to C. So if I take all those points that are close to C and I plug them into F, then the result needs to be close to F of C. But that's B. So what I can say is, because of the continuity, this F of this ball is contained within a ball that is centered at B and has radius epsilon. Okay. So what this is saying is, another way of putting it is, F of anything that's sufficiently close to C is that's this close to C is this close to B. Okay. All right. So that's just one consequence of continuity. Okay. And so really, I can't take a delta epsilon definition of continuity and just rearranging it to give me this. Okay. Now, my fixed point C is stable. So what that means is there exists a delta naught such that if I take points within this ball around C as initial data, and I plug them into the flow of X, then these are going to be contained within a ball around C of radius epsilon naught. So for whatever epsilon naught I have, I can find some delta naught. So in other words, points that are close to C, when I take their flow of them, they're going to be sufficiently close to C. So this is just a consequence of a definition of stability, which says that the limit as X approaches C of the flow of X equals C. So by taking that definition and expressing it like in epsilon delta form, you get this. Okay. So points that are sufficiently close to C when flowed are also close to C. Okay. Now, once again using that F is a homeomorphism, and therefore F inverse is a homeomorphism, I can do something similar to this. I can say that, okay, I'll typo in the notes again, but it exists a delta greater than 0 such that by taking points near B and plugging them into F inverse, by the continuity of the inverse, I can get points that are near F inverse of B, but that's C. Okay. All right. So points sufficiently close to B are mapped by F inverse to points that are close to C. That's just straight continuity. Okay. So now, to cap the proof that B is stable, I can say that the flow of Y, so basically I want to mimic this, except I want the flow of Y, and where I have C up here, I want B. So I take points that are sufficiently close to B, and I flow them up to time t. And the thing is, now I'll use a definition of the flow of y in terms of the flow of x. So that's going to be f flow of x, f inverse of this same ball. Two, three, four. Okay, so 4 parentheses. Okay. Now I can use all my subset relations that I've built up over all this time. So f inverse. Well, actually, I'm going to. Yeah. Okay. Yeah, so I'm going to work from the inside out. So f inverse of this ball is contained in this ball. Okay. But then the flow of this ball is contained within this ball. But then for my first subset relation, f of this ball is contained within this ball. So now, the relation that I have, the flow of this ball is contained within this ball. It's a radius delta on that side, radius epsilon on this side. Compare this to that. What I get as a consequence of C being stable. It's exactly the same, except instead of flow of x, I have flow of y. Instead of C, I have b. Instead of delta naught and epsilon naught, I have delta and epsilon. It's exactly the same statement. For C stability, now says the same thing for B stability. So I can conclude from all this that B is a stable fixed point of y due to C being a stable fixed point of x. So breaking down the flow of y in terms of f inverse, and flow of x, I've been using the fact that f and f inverse are both continuous to show how values near C and B are mapped, and also for this part, taking advantage of the stability of C, putting all those three things together gives me stability of B. And if you want, you could just go through the same steps in reverse, or just reverse the roles of f and f inverse in the flow of x, flow of y, to show that if B is stable, then C is stable. So there's no point in doing all that. Okay. So yes, Haley, I did turn off my ringer.
I know, yeah.
Okay.
I was just testing.
Okay. Thank you, I think.
No,
Okay.
it was my own selfish reasons.
So now, the only thing left is if I assume that C is asymptotically stable, showing that B is asymptotically stable. So that will also be an if and only thing. Okay.
Can you not just edit this proof to make it a asymptotically stable?
Not really. The definition is too different. It's not, and it's somewhat similar steps. But yeah, it's not like the simple editing that would happen if you go from B stable to C stable. All right. So now we'll assume that C is asymptotically stable. Okay. So what that means is the limit as t goes to infinity of b a flow of x equals c for all x in a ball centered at c with a certain radius, which I'll call delta naught. So that's what the definition of asymptotically stable gives us. Okay. So now, if I use similar relationships as before, so I guess maybe you can somewhat edit this. F inverse is a homeomorphism. So that tells me that F inverse of a ball centered at B of radius delta is contained in the ball centered at C, radius delta naught, for some delta. Alright, so again, that's a straight continuity. Alright. Okay. So, now I can look at, I want to take this same limit, except flow of y. Okay, so on flow of y, of little y, and I'm going to assume that y belongs to a ball centered at B of radius delta. Okay. So, now I use my definition from a previous board of a flow of y in terms of a flow of x. So that's going to be f of flow of x, f inverse of y. So I need to show that this is going to be B. So that would give me asymptotic stability. Okay, well, f inverse of, so what I can do is, whoops, sorry, I forgot a limit. This is the limit of all this as t goes to infinity. All right, now, first of all, f is continuous. So what that means is I can move this limit inside the f. So that'd be limit of the flow of x. Now f inverse of y is just x. Now the thing is, because y is contained in this ball, centered around B, radius delta, I can say that x belongs to this ball, centered at C of radius delta naught. Okay. So because of this relationship. And because of this, for any x in that ball, because C is an asymptotically stable fixed point, this whole thing, that's just C. But f of C is B. So I'm done. So that means that B is asymptotically stable.
Could you do the second last step? Like,
Oh, from here to here?
yeah.
Okay. So what happens is, okay, there's a few things that went on here. Now, because y is in this ball, but I took f inverse of it. So x is f inverse of y. X, therefore, is in this ball because of this relationship right here, due to f inverse being continuous.
Right.
Now, because C is an asymptotically stable fixed point, this limit right here is right here. So for my assumption gives me this.
Right.
Yeah. So that's how C falls out of all that. But then f of C is B.
So it's B also.
And the thing is, a lot of proofs work this way, where you're taking your assumption, you're translating that into an equation that you can use, and also, what is the conclusion you're trying to reach? Your conclusion you're trying to reach is that B is asymptotically stable. Well, what's the definition of that? You want to show that this limit is B. So once you're doing all the translating just from the words, is you want to show that this limit, being C, implies that this limit equals B. Well, how are you going to get from here to here? You need a relationship between the flow of X and the flow of Y. That's our relationship. So you use that in order to get from what you're assuming to what you're trying to prove. And especially in classes anyway, where the proofs are, yes, some can be more involved than others, but most of the time, just from what I've seen students show me from problems they get in other classes too, like modern algebra or whatever, or real analysis for that matter, is that you have this, here are your assumptions, get equations, here are your conclusions, get equations for those, describe them that way, and then how do all these entities relate? And those relationships come from usually other results that you've already seen. Unfortunately, there's no way to really have a systematic algorithm for proofs, but if there were one, it would be something like that. Okay. Now, from this result that if you have two systems that are topologically equivalent, that their fixed points have the same kind of stability, I can now state the main result, and unfortunately there's no need to really bother proving it, of this section. What can you say about the stability of a fixed point of a nonlinear system? So I'm not going to finish the whole course in 8 minutes. 7 minutes, but oh well. But at least I know from how far I'm getting in the notes that Monday will definitely be the last. Okay, well, unless you guys want to show up the following week for homework questions. I'll be here anyway. Okay, so really it's a corollary of this proposition. Okay, actually I do have a proof here, but it's really short. All right, so let's suppose that C is a fixed point of X. And let's suppose that our Jacobian of X, evaluated C, so there's a Jacobian matrix, has eigenvalues with, for real parts, and I'm just using lambda as a standard symbol for referring to an eigenvalue. If all the eigenvalues of x prime of C have negative real part, then C is asymptotically stable.
Watch it.
Oh shit. Okay. Wow, that's really weird.
Sacrifice your phone.
The coefficient, the sliding coefficient.
Is your phone
Oh,
okay?
yeah, it's fine.
Okay.
I don't know, this one doesn't break from knock on wood, but.
Okay, well that's good. All right. Okay. Well, thank you for catching that, because I would have. Okay. All right.
There's a very interesting video if we would have kept on recording on our channel.
Yeah, I don't get it. Yeah, probably give a viewer like vertigo or something like what?
Oh no, just you scream. Ah!
Yeah.
Lots of editing.
Yeah. Okay. So if a Jacobian C has negative eigenvalues, then it's asymptotically stable. And then the other part of this, based on linear theory, is okay. If the same Jacobian matrix has any eigenvalue with positive real part, then C is an unstable fixed point. So all it takes is one. Okay. Oh. Sorry, I made a mistake here. C has to be not just any fixed point. It has to be a simple fixed point. And what that means is that the determinant of a Jacobian matrix is non-zero. So there are no zero eigenvalues. So, okay, so we just have to make sure about that. Okay. Now, because this deals with the linearization theorem. So, because C is simple, that means that this system, x prime is big X little x, and y prime is a y, are topologically equivalent. Where A is Jacobian. So we need to make sure we've got the topological equivalence, and this is a consequence of a linearization theorem. Okay, so the thing is, if you don't have this condition of C being a simple fixed point, you might not have a topological equivalent, because I showed examples of that where you have non-simple fixed points, and the linear and nonlinear systems do not have the same character at all. So that's why the condition of C being a simple fixed point is so important, so that the linearization theorem actually applies. Okay, the thing is C. So the consequence of that, C and 0 have the same stability. So now you can determine the stability of C by discussing the stability of 0. And 0, you can use just a linear stability theory. That if all the eigenvalues of this matrix have negative real parts, 0 is an asymptotically stable fixed point of this system. Therefore, C is an asymptotically stable fixed point of this system. And then if one eigenvalue of this matrix is positive real part, 0 is unstable. Therefore, C is unstable.
That only applies when C is simple.
Right, only when C is simple, because otherwise you cannot make the leap from this system to this. You can still make the same conclusions about 0, you cannot apply those conclusions to C. Okay, and that concludes section 6.3. So I have 2.5 pages of notes left. And I will definitely be able to finish that on Monday, and time is up anyway. So it looks like the rest of the recording was okay. So enjoy analysis. Is it a 2-hour class again?
Yeah, we got class in
For now.
2 minutes.
Oh shoot, I forgot about that. Sorry. Okay.